Okay, so the basic idea of this direct power injection method is that we are directly injecting RF power into an IC. In this case, by a coupling capacitor. So we are using not inductive coupling with this bulk current injection, we are now using capacitive coupling over a capacitor. And here comes the interesting thing. I can place a very, very simple capacitor next to the IC pin, and then I can directly inject into the IC pin. And this is the basic idea. So it needs a signal generator, power amplifier, injecting capacitor. Here it says DC block, and an IC under test. So this capacitor here actually has multiple functions. One is acting as a capacitive coupling device. But let's suppose we are injecting into the power supply pin of the IC. High side switch. We have 13.5 volt power supply. And without the capacitor, we would use a signal generator, power amplifier, and connect it directly, because the standard says direct coupling, directly the output of the power amplifier to the power supply pin of 13.5 volt. Might not be that good for the output of the power amplifier, because we have 13.5 volt directly at the output. So therefore, we also need a DC block. And this coupling capacitor acts also as a DC block. Very simple. We just have to take care that the coupling capacitor has the right voltage values, DC operating values. Because on the one hand, the capacitor should be as high frequency, or as low impedant over a wide frequency range as possible. But on the other hand, it should be DC voltage stable and offering a wide DC voltage range. And very often engineers don't think of the DC operating ranges. They say, I need a capacitor up to, okay, the standard says 1 gigahertz, but I want to tweak a little bit into the higher frequency range, so I'm using a smaller capacitor from the package size. You can remember we talked about what is limiting the frequency range of the capacitor. It's not the value itself, it's the size of the capacitor. So if it's a 12.6 or a 0805 package, so the package. And then very often they're using a very small package to increase the frequency range. But then this is then maybe just a 5 volt capacitor or whatever. And then they are injecting into a DC-DC converter power system with a DC voltage potential of 250 volt. And then the capacitor is not acting as a DC block anymore. Okay, so please take care. So the capacitor has multiple functions, and the big advantage is it's a very simple test setup, has a very high degree of repeatability. We can also make pin selective measurements. Clear, we can inject only in one pin, but we can also inject in multiple pins. I'm not sure if you can read this. Usually the ICs under test are defined in different zones. So there is, let me see it here a little bit clearer. Here it is. I'm coming back to the slides that I was jumping over. There is zone 1, which defines, for example, ICs like this automotive high-side switch, which have somehow a direct connection to the cable harness, driving directly a signal out of the printed circuit board into the cable. For example, CAN bus driver, LIN bus driver, this high-side switches for driving the front light, because there is the control box and there is a cable going to the front light, and inside of the control box is this IC. So, and then usually these ICs are then also can be exposed to high interferences, because the cable harness acts as a receiving antenna. And therefore, it's very important that we are characterizing this IC up to very high power levels. And the power levels go up to 30 to 37 dBm, which is 1 to 5 watts. And this is quite a lot of RF interference power that we are providing to the IC. Let's suppose we have a very small microcontroller in the what's the English word for? A very energy efficient microcontroller consuming microwatts, and now we are driving 5 watts of RF power in the direction of the microcontroller. But that's the way it is. Okay, then in zone 2 we have ICs which usually do not have a direct connection to the cable harness, but also are very important, like ABS sensor ICs, sensor conditioning ICs, communication line drivers. Very often these ICs are then additionally protected by somehow external filters, and they are usually operated or interfered by 20 to 27 dBm. And then in the third zone we have ICs like this microcontroller, which usually does not have a direct connection to the cable harness. It's just connecting to another IC on the same printed circuit board, but not leaving, or the pins are not leaving directly the cable harness. And this is then, or the maximum power amplitude that we are providing is then 10 to 17 dBm. Okay, then let's go back to the slides that I was jumping over. So here you can see the basic test configuration. So let's start here. We need a signal generator, a power amplifier, a directional coupler to measure the forward power and maybe also the reflected power. We are coming to that. And then we are directly connecting this coaxial cable from our noise source, in this case, very often by a coaxial cable and an SMA connector, to our printed circuit board. And from the printed circuit board, we have then a printed circuit board trace, 50 ohm trace, to our capacitor. And next to the capacitor is then the IC under test, the whatever input pin or whatever we are testing. So you can see here. So let's suppose it's the power supply pin. So this power supply pin has to be connected to a battery. Yeah, but in this case we also need a decoupling network, because if we are directly injecting our signals via the capacitor into the power supply, we want that our noise signal really goes into the direction of the IC and not being shorted directly by the battery to ground. So therefore we need a decoupling element between the battery and our injection point. And in the side of the standard, it's also defined that this decoupling network should have a frequency characteristic all over the frequency range of higher than, I think, 300 ohms or 1 kilo ohm. I think 1 kilo ohm over the whole frequency range. So to make sure that the RF energy really goes inside or into the direction of the IC and not being shorted, I think this is clear. Okay, so forward power, reflected power. Why is this important? So in the table before, you have seen that we have quite a lot of power that is delivered to the IC, which very often gives the engineers the impression that this is really the power that we are forcing through the IC. We are forcing it into the bin, and then every current flows in the bin and comes somehow out of the bin. Actually, this is not really the case, and now it comes to the important thing, so please take care now. This is only the power that we are providing to the IC in a pure 50 ohm system, as good as possible. So we have a 50 ohm system at least up to here. Then here there should be a 50 ohm microstrip line, and also from the capacitor to the IC pin we should also have a 50 ohm microstrip line. Okay, the capacitor itself doesn't have 50 ohm, it's clear, but it's in series, so it's not that critical. And now what's happening here, exactly at this edge here, here we have the input impedance of the IC. Okay, is the input impedance of the IC 50 ohm all over the frequency range? Most probably not. So what does this mean? We have a very big mismatch exactly here at this point, also here at the input impedance of the IC. Which means that the 37 dBm that we have seen before for ICs directly connected to the cable harness is not really 37 dBm that goes into the IC. it would go into the IC and dissipate it into heat in the IC if the input impedance of the IC would have been 50 ohm. But it's definitely not 50 ohm. So much, or the most of this RF energy that we are providing will be reflected back. It will be reflected back exactly here. So only a fraction of this noise that we are providing, or of this disturbance signal that we are providing really goes into the IC and then heating up the IC or whatever happens. So although we have very high power levels, the IC itself will never ever really see these high power levels because most of the power will be reflected back. So therefore sometimes it's also interesting to see how much power is reflected back. And then from the difference between the forward power and the reflected power, we can also get some information how much power is really dissipated in our system.
Does it really make a difference if you use a 15 impedance line or just whatever, a trace which can hold the carrying current?
Yeah, thank you. Very, very good question. In the ideal case, it would be perfect to have really a 50 ohm microstrip trace, for example, to the IC pin. But the IC pin also needs some external circuitry, and if it's a power supply pin, for example, for these automotive powers, smart high-side switches, the power supply pin is about this big. It's not that small. There are 5 pins connected in parallel for the power supply, for example, or the whole drain metal area is the power supply. So this is anyway not a 50 ohm system anymore when it's used in a printed circuit board. So therefore, we at the Institute, we are trying to keep the high frequency injection line 50 ohm as good as possible until we are reaching somewhere the area where we are close to the IC pin, because there the IC pin has to be connected to whatever is outside anyway, and whatever is outside is anyway not 50 ohm. Yeah, but this really makes this measurement technique then also not that super reproducible, because it really depends on your skills in high frequency design. And just yesterday we were sitting together with a bachelor student who is designing now such modular boards, how to make the system as 50 ohm as possible, which is not that easy. So, and the standard doesn't give that much information. It's just, use a 50 ohm microstrip trace to the IC pin. Yeah. And yeah, maybe coming back to your question and trying to answer the question. So if it still then makes that much sense to keep this part of the line 50 ohm, when all these parts here, power supply, for example, is a very big line because you need to have amps over the power line, I think it's not that critical anymore. But we are trying to keep it as 50 ohm as possible up to here, and then depends. Okay, so what is also important, we need a control PC and a very good monitoring system that is checking if this device is still working properly. And as I said, monitoring is complicated, yeah. Imagine this is a microcontroller. And now you have to monitor the whole microcontroller to make sure that in all operating states, whatever the microcontroller is doing, everything is working well, fine, as defined, as specified in the standard, or as specified in the datasheet. Monitor all the registers, all the thing, so it might be a little bit, quite a lot of work to do. So therefore, the skill is to define really good monitoring criteria that gives you, on a first hand, a lot of information. Is your IC okay or not? But this is, as I said, very complicated. Okay, the whole procedure is also defined in the standard. It says start at the starting frequency, 1 megahertz, increase step by step the amplitude until something is not working anymore. And then, go to the next frequency position and again increase from low levels up to high levels. So there are 11,000 something measurement points all over the frequency range. Because you cannot jump from 1 megahertz to 10 megahertz, 100 megahertz, 1 gigahertz, and everything is fine. Because it can be that there are narrowband effects in your IC, and there is just one certain frequency position, the 15th harmonic of your internal clock signal, where the IC is very susceptible. And if you're not testing exactly at this frequency, you will never ever figure out that there is a problem. So you also have to define very small steps in order to capture the whole frequency range. And then on every frequency position, you have to increase the amplitude and wait at every amplitude and frequency position. How long? At least 3 times the operation cycle of your IC. Okay, now you have a microcontroller, which is most of the time in sleep mode, and then just waking up, doing something, falling again into sleep mode. So you have to wait until at least 3 times until the microcontroller is waking up, doing something. Because it could happen that in sleep mode, the microcontroller is very robust. Yeah, and then over the whole frequency range, you have measured at 3, 4, 5 different amplitude and frequency positions the microcontroller when it was not in sleep mode. So defining this whole procedure and the monitoring and making sure that everything is working and running is a little bit complicated. Okay, so just let me check how much time we have. Uhr, 5. Okay, sorry for running overtime. Then I'm just finishing this with the DPI. So this is how a typical DPI dashboard looks like. So here we have our device on a desk. Here is the 50 ohm injection line. So we have tried to keep it 50 ohm as good as possible up to this point here. And here it's, in this case it was the out, this is the output of the chip. So here we have a big metal area which is connecting all the output pins. Then here is our decoupling element for the output, because we do not want to short the RF signal via the output load. We want to inject the RF signal into the output pin. So I'm pretty sure that this metal plate here doesn't form a 50 ohm system anymore, but that's the way it is. I cannot come over that. Yeah, and here are all the external components that are needed to operate the IC. This big inductance here and here, these are the decoupling elements. One is for the power supply, the other one is for the output. Yeah, so there is a lot of skill in designing this printed circuit boards. Yeah, this is the setup that we are using. Standard setup, we have a signal generator, a power amplifier. This is the directional coupler. Here is the SMA cable that injects the RF signal into the printed circuit board. Here, in this case, we are measuring the forward power. The forward power is the thing that you are then displaying on your susceptibility characteristic. Yeah, and quite a lot of monitoring stuff in order to figure out if this IC is working or not. Yeah, this is then the final result. As I said, we have started here, going up, and in this case, we have tested a smart high-side switch in order to figure out if a functional safety criteria, in this case the over temperature detection under RF interference, is still working. And unfortunately, it's not working that well. Because here we can see at a frequency of about 2.2 megahertz and 13 dBm. And this is a smart high-side switch, which is directly connected to the cable harness. So it should, as we have defined in the zones, at least be susceptible up to amplitude ranges of 30 dBm, better 37 dBm. So actually, this curve should be within this range here or here. And our device that we have characterized was failing at 13 dBm, providing an incorrect information of the overtemperature sensor system, which means that even at this low disturbance value, the overtemperature detection was not working correctly, and the control unit did not realize that the IC is in overtemperature, which is really a severe functional safety issue. And now the automotive industry is a little bit concerned about these things because quite a lot of smart power devices that are currently on the market, and there are billions of these devices in modern cars, might face same issues, so that their internal protection and functional safety features are not that robust and reliable when they are tested with RF interferences. But this is another story because actually there are not so many EMC experts who are testing ICs in overtemperature and checking if in overtemperature everything is fine. But we as a university, we are trying to figure out what are the weaknesses of ICs. And this was a very simple and very cool example where we could show that ICs which have smart functional safety features are not that smart when it's about RF interference anymore. This is a little bit a problem.